Hi everyone, welcome to our video on how to do a one-sample t-test in R. Just to get a few things out of the way up front, so this video is strictly about doing the test in R. We're going to assume that you already understand the theory behind the t-test and have kind of the statistical foundations down. We're also going to assume that you have some basic principles of R down, so just how to import the data. So if you're unfamiliar with those things, please go check out some of my other videos on those topics. But the focus for today's video is strictly about kind of running the code for doing a one-sample t-test and how we might visualize some of those results. I'll also mention that in the video description, there's a link to this script file on my GitHub repository. Okay, so if we're going to do a one-sample t-test in R, the first thing we're going to need to do is import some data. So I'm going to load a couple different libraries. We won't use all of them or most of them necessarily here. But we are going to use tidyverse mostly to get access to ggplot in order to make some graphics. And then we're going to use the other libraries and some of the other how-to videos later on. So we're just kind of getting in the habit of loading those libraries. Next, we're going to read a CSV file from the web and import that file and call it data. And if we take a look at the head of that file, you can see that these are different students who were taking either an ACT prep course or not taking an SAT prep course. And then we ascertained their scores on the SAT. So in this data set, ultimately we're really going to be interested in the difference between those students who took the course and the students who did not take the course. But for the one sample t-test example we're going to do today, we're just interested in if these students scored above average on the SAT. And this example was created a while ago, so I'm not really sure if these data apply to the way that the SAT math section is scored anymore. But we've got a distribution of scores here that we can get using the histogram function. And so again, this is regardless of group. This is just referring to all of the 20 students in our sample. If we want a basic one-sample t-test in R, we can just use the t.test function, and we don't have to actually specify any other arguments. By default, it's going to return a one-sample t-test, as you can see in the output down here. The t specifically was 81.5. With 19 degrees of freedom, and that has a pretty small p-value, 2.2 times 10 to the negative 16th. So this would be a very unlikely result if the null were true. So we're probably going to reject the null hypothesis and instead accept the alternative hypothesis that the true mean of this sample is probably not 0. But, of course, that's not actually really that surprising for the SAT, because getting an SAT score of 0 is incredibly unlikely. So a null hypothesis test in which we assume 0 is not really the most meaningful as a null hypothesis test. So the other thing that we might want to do is assume a non-zero null against which to test our data. And this is also sometimes referred to as a minimum effects test. Right, but what we're trying to do in this non-zero null is see if the mean of our data, which happened to be 591, is statistically different from some hypothetical true value of the mean. And so in this case, we'll call that 600, which I believe at the time that this example was created was kind of the average SAT math score. Now, if we do that, you can see that our mean of 591 is actually no longer that statistically different from a true mean of 600. Before, it was very unlikely to observe data that we did when we assumed the true mean was 0. But of course, assuming that a true mean of 0 for the SAT math test doesn't make a lot of sense. So in this more realistic example, where we're trying to say, did our sample deviate from the national average of 600, we don't actually find any really reliable evidence that our sample does not belong to that population. 600 is a pretty reasonable value as the true value in the population, because as you can see, we only would have observed a mean of 591 or less about 22% of the time if 600 was the true value. Now, the other thing that we can do is actually make a one-sided test of this hypothesis. At the moment, we're doing a non-directional or a two-sided test, where we're interested in if you're falling either above the null value or below the null value. But what we can also do is assume that the true mean is less than or equal to 600, or we could assume that the true mean is greater than or equal to 600. Now, the syntax here for the one-sided test is a little bit different, because rather than specifying the null, you actually specify what your alternative hypothesis is. So if the alternative hypothesis is that the mean we observe is greater than 600, we would specify alternative equals greater. But note, that's the same as saying that the null hypothesis is that the true mean is equal to or less than 600. So if we do that, you can see that again we have a very large p-value here because of course 591 is less than 600, so it's going to return a very large p-value. This is very consistent with our null hypothesis, right? Our null hypothesis was that the true value is equal to 600 or less. What we observed was less than 600, therefore it's not statistically surprising under the null hypothesis. If we flip this around to do a directional test the other way, now we're assuming that the true value is actually greater than or equal to 600. Well, 591 is less than 600, and we're going to get a p-value that is smaller, right? This is more statistically surprising considering that we had a null hypothesis that the true mean was greater than or equal to 600. Finally, if we want to visualize these data, we might want a few different types of visualizations that are perhaps a bit more informative than this simple histogram, or even if not necessarily more informative, at least give us a slightly different way of looking at the data. So another thing that we can do is convert that histogram into a density plot, but using the layering that's available to us with ggplot2, we can now not only show the distribution of the data overall, but we can show those individual data points. And then we can use this geom v line to draw a line at 600, or wherever we're going to set our null value. So this would kind of allow us to see the distribution of the data relative to the null value. Alternatively, if we want a plot that actually gives us a little bit more information about how to make our statistical inference, we could draw a dot plot with error bars. Not a box and whisker plot, but a dot plot with error bars. And you can see now we have a dot representing the mean. And then I've drawn these whiskers out to be the standard error. So this represents one sampling standard deviation for the mean in either direction. And you can see, obviously, the mean we observed is included inside of that one standard error. So what we observed is well within sampling variability, assuming a null hypothesis of 600. Alternatively, we can take this a step further and kind of keep the same overall plotting aesthetic, but rather than looking at error bars, we could look at something like the 99% confidence interval. So in order to do that, we first have to determine what the t critical value is, which is based on the degrees of freedom in our data set. So we're going to calculate the t critical value first. In this case, it happens to be about 2.09. And then we're going to be able to calculate exactly what the confidence interval should be going in either direction. We can then plot those data. And now you can see that we have a 95% confidence interval rather than the single standard deviation going off in either direction. Again, though, not surprisingly, right, our null value of 600 is well within the 95% confidence interval, consistent with the p-values we were seeing before. It's very likely that we observed a mean of 591 if the true mean in the population were 600.